A resistor's main job is actually pretty simple. It turns electricity into heat. But here's the catch, and it's a dangerous one. If that little component can't get rid of the heat fast enough, it can literally blow up in flames. So today, we're going to break down exactly why that happens, and more importantly, how you can make sure it never happens to one of your projects. Okay, if you've ever messed around with electronics, I bet you know that sinking feeling in your stomach when you see that little puff of magic smoke escape from a component. It's frustrating, right? And maybe a little scary. Well, we are going to demystify that moment today. Turns out it's not magic at all, it's just pure physics. And almost every single time, it comes down to ignoring one simple number, the wattage reading. Focusing only on the ohms and forgetting about the watts is basically a recipe for disaster. Let's dig into why. So what is actually happening inside that tiny component? Well, resistors are designed to make it harder for electrons to flow through a circuit. They're literally resisting the flow. And doing that, they remove energy from those electrons. But that energy has to go somewhere, right? It doesn't just vanish, it gets converted directly into heat. And that light bear brings us to the most important concept here, the power rating, which we measure in watts. Now, this number has absolutely nothing to do with how much it resists electricity. That's what ohms are for. The wattage tells you one thing and one thing only. How good is this resistor at getting rid of heat? It's all about its heat dissipation capability. I want you to imagine a massive traffic jam, but for electrons. The resistor is like closing 3 lanes of a 4-lane highway. As all those electrons try to squeeze through that tiny bottleneck, they're constantly colliding with the atoms of the material inside. And every single one of those little collisions generates heat. Alright, this is where a lot of people, especially when they're starting out, get tripped up. It's so easy to look at a physically big, chunky resistor and just assume it must have a really high resistance value, a lot of ohms. But that's not how it works at all. See, the physical size of the resistor is all about surface area. The bigger the resistor, the more surface area it has to radiate heat away into the air. That's what gives it a higher wattage rating. The actual resistance, the ohms, well, that's what the little color bands are for. This means you can have a tiny little resistor and a massive one with the exact same 100 ohm resistance. The only difference is how much power they can handle before they burn out. You know those little guys you get in hottie kits? The common carbon film ones? Those are typically rated for 1/4 of a watt, maybe half a watt. The teeny tiny surface mount resistors you find on your phone's circuit board, even lower. But then you see those big, beefy ceramic or aluminum case resistors. Those things are built like tanks to dissipate serious heat. We're talking 10, 50, even hundreds of watts. Okay, so how do we actually avoid a meltdown? Well, the good news is it's not guesswork. It all comes down to some really simple math. Let's walk through how you can calculate exactly what your circuit needs to stay safe and reliable. It's really just a straightforward 3-step process. First, you've got to figure out the current, which we call I, that's going to be flowing through that resistor. You can usually get this with Ohm's law. Second, you need to know the voltage drop, V, across that specific resistor. And finally, you just multiply those two numbers together. Power equals voltage times current. That number you get is the power, in watts, that your resistor is going to be turning into heat. Let's make this real. Imagine you got a 9-volt battery. In our first safe scenario, we're using a 1000 ohm resistor. This is just a tiny bit of current, and the total power we need to get rid of is just 0.081 watts. No problem, any standard resistor can handle that. But look at that second scenario. If we swap in a 10 ohm resistor, the current just skyrockets, and the power, a massive 8.1 watts. And this is the whole point right here. 8.1 watts is more than 16 times the half-watt limit of a standard little resistor you'd get in a kit. When you try to force that tiny component to dissipate that much energy, the heat goes up so fast it literally has nowhere to go. The result? That protective coating is going to char, smoke, and catch fire. So all of this leads to one final super important takeaway. There is one simple golden rule that's going to keep your projects reliable and, not on fire. It all boils down to this: giving yourself a safety margin. A simple rule of thumb that makes sure you are never, ever pushing your components to their absolute breaking point. And sure it is, always, and I mean always, choose a resistor with a power rating that is at least double what you calculated it will need. So if your map says it's going to dissipate 0.4 watts, do not use a 0.5 watt resistor. Yeah, it might work for a while. It's going to run burning hot to potash, and its lifespan is going to be way shorter. If you use a 1 watt resistor instead, it'll run nice and cool, last for years, and make your whole circuit way more reliable. So let's just boil this all down into 3 simple actions you can take every single time. 1. Calculate your current. 2. Use the power formula, P equals V times I to find a watts. And 3. The most important step for long-term reliability, double it. Get a component rated for at least twice what E. So it kind of leaves you with a final question to chew on, right? We usually think of resistors as these simple little things that just minute current. But when you really understand power readings, you realize their job is way more active than that. They are in fact purpose-built heat management tools, and choosing the right tool for the job is what separates a reliable project from a little fire hazard.